So today I want to talk to you about domain number 3 out of the CISSP exam. We're going to do a deep dive into this domain, the security architecture and engineering. It counts for 13% of the total questions on the CISSP exam. It deals with various topics such as separation of duties, threat modeling, failing securely, shared responsibilities, defense in depth, as well as identifying different security concepts and models, such as the Biba model or the Bell-LaPadula model. It also teaches the security practitioner to assess and mitigate vulnerabilities of security architectures, design solutions, and elements. It's very important that you understand this. It's very important that you have a firm grasp on these topics. Tap in for this one. We got an hour and 20 minutes. Hacker Black, CISSP, Domain 3. Let's get it.
Domain 3, Security Architecture and Engineering. Module 1. Processes using secure design principles. Module objectives. 1. Implement engineering processes using secure design principles. 2. Manage engineering processes using secure design principles. Systems engineering versus systems security engineering. Systems engineering is method of developing and managing the development of complex systems. Rockets, cars, power plants, etc., by breaking the larger idea in smaller pieces that can be developed and tested singularly and, as they work together to form the whole system, the system will come together and meet functional requirements. Systems security engineering are the supporting efforts that protect the CIA of the systems and its components, not relating to function of the system but the security of the system. System and security engineering processes. Commonly accepted sources for engineering processes. International Council on Systems Engineering, CISSP 800-160 Systems Security Engineering. ISO IEC 15026 Series Systems and Software Engineering. ISO IEC/IEEE 15288 Systems and Software Engineering. Systems and systems security engineering processes have converged across major sources. NIST and COSI recognize systems security engineering as a specialty engineering function. What is systems engineering? SEV model. V model, understand the system engineering lifecycle which is depicted by V model. The left side of the V depicts project initiation such as requirements, detailed design, etc. The base of the V depicts implementation. The right side of the V depicts project testing and integration, test, verification, validation, operations and maintenance. Technical processes. Business and mission analysis process. Stakeholder needs and requirements definition process. System requirements definition process. Architecture definition process. Design definition process. System analysis process. Implementation process. Integration process. Verification process. Validation process. Transition process. Operation process. Maintenance process. Disposal process. Technical management processes. Project planning process. Project assessment and control process. Decision management process. Risk management process. Configuration management process. Information management process. Measurement process. Quality assurance process. Enabling processes. Lifecycle model management process. Infrastructure management process. Portfolio management process. Human resources management process. Quality management process. Knowledge management process. Agreement processes. Acquisition process. Supply process. Module 2. Fundamental concepts of security models. Module objectives. 1. Identify the purpose of security models. 2. Identify common security models. Security models. Purpose: security models define rules of behavior for an information system to enforce policies related to system security but typically involving confidentiality and/or integrity policies of the system. Security models examples: Bell-LaPadula, confidentiality; Biba, integrity; Brewer and Nash, confidentiality; Clark-Wilson, integrity; Graham-Denning, confidentiality/integrity; Harrison, Russo, Ullman, integrity; Bell-LaPadula, BLP, confidentiality state machine model. Developed for Department of Defense, DoD, used for multi-level security, MLS3 properties defined. No read-up, simple security property. No write-down, star property. Access matrix, discretionary security property. Biba, integrity state transition model. Focus on integrity vice confidentiality. Opposite rules from Bell-LaPadula, VLP. Read-up, simple integrity property. Write-down, star integrity property. Lower level process cannot request higher access, invocation property. Brewer and Nash, confidentiality. Designed to prevent conflict of interest. Information flow control model. Decomposes a company's information into discrete datasets based on potential conflicts of interest. Defines rules for acceptable access to data objects by a particular subject, for example, person or process. Accessing a data object excludes future access to potential conflict of interest objects. Clark-Wilson, integrity introduces the concept of triples. Subject, program, object. Subjects can only manipulate data objects through the use of a defined program. Set of rules designed to ensure data integrity for all operations. Graham-Denning, confidentiality/integrity set of rules for creation, assignment of access rights, and deletion of objects and subjects. 8 rules: create/delete object/subject, assign, read, grant, delete, and transfer access rights, often used in distributed systems. Harrison, Russo, Ullman, HRU, integrity primarily for protection of access right integrity. Confidentiality is protected by access rights, so HRU does provide secondary confidentiality protection. Extends Graham-Denning model. Defines a set of primitive allowable operations involving subjects and objects. Modern implementation. Various components of security models are integrated into modern operating systems, OSs. The access control mechanisms discussed in Domain 5 implement key features of the security model in practical systems. Security models may not be implemented exactly in modern systems, but they provided the basis for most modern security implementation. Module 3. Select controls based upon system security requirements. Module objectives. 1. Differentiate between security requirements and security controls. 2. Identify types of controls. 3. Identify common or inheritable controls. 4. Select appropriate security controls. 5. Identify major control frameworks. 6. Tailor security controls. 7. Identify security control evaluation criteria. Security controls. Safeguards or countermeasures that mitigate risk to confidentiality, integrity, or availability in a system or operating environment. Controls may impact or modify the behavior of people, process, or technology. Types of controls. Control action types. Preventive controls. Reduce likelihood or impact of an undesirable event occurring. Detective controls. Identify an undesirable event or collect information about it. Corrective controls. Reduce or eliminate the impact of an undesirable event that has occurred. Means of application. Management. Policy or human-driven controls. Operational. Process-driven controls. Technical. Controls applied to technology. Common/inheritable controls. Common or inheritable controls exist outside of a particular system but provide some confidentiality, integrity, or availability protection to the system. For example, enterprise firewall protections are inherited by systems behind the firewall. May include management, operational, or technical controls. Control selection. Controls are selected to support the confidentiality, integrity, and availability needs of the system. Control frameworks are often utilized to select appropriate controls and define controls. Inheritable controls that support the system are identified. Control frameworks. Control frameworks define controls and control elements. Frameworks allow for standardization of control implementation. Control frameworks often include evaluation criteria or mechanisms to verify controls are effective. Example control frameworks and standards. ISO IEC 27001 is an international standard. NIST, SP 800-53, is required for U.S. government use. COBIT is focused on business values. ISA IEC 62443, ISA 99, deal with industrial automation and control systems. Tailoring controls. Control frameworks and standards are intended to be tailored to specific use cases. Adjust control specifications or parameters to meet the needs of a specific system or environment. Book controls must be tailored to provide optimal value. Important. Controls are not intended to be checklist items, but some organizations treat them as such. Evaluation criteria. Each control should include specific evaluation methods and expected results. Example evaluation methods from NIST. Test. Conduct a direct test of the control, usually used for technical type controls. Interview or question staff, usually used for management or operational controls. Examine documentation or artifacts for evidence that a control is properly employed, used for all control types. Controls may be evaluated by multiple methods. Module 4. Security capabilities of information systems. Module objectives. 1. Identify types of system security capabilities. 2. Employ integrated security elements. System security capabilities. Access control. Processor states. Memory management. Process isolation. Data hiding. Abstraction layers. Security kernel. Encryption. Code signing. Audit and monitoring. Virtualization/sandbox. Hardware security modules. File system attributes. Generic operating system, OS/computer model. Access control. OS controls access to objects. Rules define allowable behavior. Security monitor or reference monitor enforces allowed behavior. File systems typically support by assigning security attributes to objects/files. Access control models are described in detail within Domain 5. Processor states. Processors typically support at least 2 states of operation. User mode. Kernel mode. User mode has limited access to core functions or direct hardware access. Memory management. Direct application access to system memory is restricted. Modern operating systems randomize memory locations, address space. Modern operating systems limit memory locations where code can execute. For example, data execution prevention, DEP, in Windows. Process isolation. Processes execute in separate memory spaces. Direct exchange between processes is limited. Operating system, OS, manages inter-process exchanges through controlled interfaces. Data hiding. Typical with multi-level security, MLS, architectures using mandatory access control, MAC. Data or objects at a higher security level cannot be seen by objects at a lower security level. Associated to the Bell-LaPadula (BLP) security model. Also a coding practice where raw data is hidden from access and can only be obtained from a standardized interface. Abstraction layers. Limits direct access to objects or entities. Defines allowable actions and interactions between layers. Protects against improper behavior or access between layers. Security kernel. Also known as a reference monitor. Big brother of kernel mode. Monitors and validates access control over system objects, for example, files, network stack enforcement and validation component of all secure operating systems. Encryption. Encryption can be applied to data at rest, for example, files on hard drive, or data in transit, for example, communication channel may protect confidentiality and/or integrity of data. Data cannot be read without the proper decryption key. Protects data when OS features, for example, security kernel, are not active or present. For example, Windows BitLocker protects data when the OS is not running and an attempt is made to physically remove and read the computer hard drive. Code signing and validation. Cryptographic function. Executable code is digitally signed. OS validates signature before loading code. Unsigned code or code with an invalid signature is prevented from executing. May include OS internal code to prevent replacement of OS components. Audit and monitoring. System actions are recorded and stored in a protected location. Audit storage protection levels vary by system and must be enabled and validated. Specific actions that are recorded are typically customizable. Audit records must be reviewed or monitored to be an effective protection. Monitoring and review may include both automated and manual elements. Audit records are typically transferred off of a system for protection and long-term storage. Virtualization/sandbox. Executing code is wrapped in a virtualization or sandbox layer. Code executing within the environment is strictly limited from direct interaction outside the environment. Permissions for system access may be restricted independently for each virtualized or sandboxed instance. May be an OS native function or function provided by third-party software. Hardware security modules. Hardware components that provide security services. Trusted Platform Module, TPM, most common security module, present in most modern hardware platforms. Provides secure storage and cryptographic functions. Typically used to securely generate and store encryption keys. Keys or stored data cannot be extracted from the module without appropriate permissions. Specialized devices, for example, cell phone, may contain multiple hardware security modules. File system attributes. Various file systems may store security attributes or provide security functions. A critical component to employing access control models in most operating systems. File systems may include journaling that can protect data integrity. Host protection software. Antivirus. Host-based intrusion prevention, HIPS host firewall. File integrity monitoring, FIM configuration and policy monitor. Module 5. Vulnerabilities of security architectures, designs and solution elements. Module objectives. 1. Identify vulnerabilities and mitigations in client-based systems. 2. Identify vulnerabilities and mitigations in server-based systems. 3. Identify vulnerabilities and mitigations in database systems. 4. Identify vulnerabilities and mitigations in industrial control systems, ICS. 5. Identify vulnerabilities and mitigations in cloud-based systems. 6. Identify vulnerabilities and mitigations in distributed systems. 7. Identify vulnerabilities and mitigations in Internet of Things, IoT. Module objectives, continued. 8. Assess and mitigate vulnerabilities in web-based systems. 9. Assess and mitigate vulnerabilities in mobile systems. 10. Assess and mitigate vulnerabilities in embedded systems. Vulnerabilities of security architectures, designs and solution elements. This module introduces some common vulnerabilities and mitigation approaches. These are common among most system types. It presents typical vulnerabilities and mitigation approaches for various system types. The vulnerabilities and mitigations are not intended to be comprehensive for each system type. For each system type, consider which common vulnerabilities might exist in the various system components. Top threat actions/mitigations. Top threat actions. Hacking. Social engineering. Malware distribution. Phishing. Top mitigations. Know what you have. Patch and manage what you have. Assess/monitor/log. Educate users. Common system vulnerabilities. Hardware. Hardware components may fail at any time. Mean time between failure, MTBF, used to calculate expected life. Failure rates higher during initial system operation. Supply chain issues may introduce technical flaws/vulnerabilities or malicious modification. Old hardware may be difficult to repair/replace. Communications can fail. Can be blocked, denial of service, DOS can be intercepted. Can be counterfeited, replayed can be modified. Characteristics can expose information about the sender/receiver, for example, address, location, etc. Misuse by user. Can be intentional or accidental. Can degrade or bypass security controls. Increases in likelihood as difficulty to operate increases. For example, difficult security requirements increase likelihood of intentional misuse to get the job done. Code flaws. Exist in all software products with more than trivial complexity. May be introduced accidentally or intentionally. Typical risk conditions. Known flaws, patch available, systems not patched, exploit available. Known flaws, patch not available, exploit available. Unknown flaws, exploit available, zero-day attack possible. Emanations. Hardware/physical elements may radiate information. Radio frequency. Visible and non-visible spectrum. Can be used to discern system functions. Can be used to locate systems/components. Desktops, laptops, then client terminals, etc. typically present in large quantities. Continuous state of adding new and decommissioning old in most organizations. General-purpose devices with inconsistent usage patterns across the install base. Physically under user control. Susceptible to user misuse, intentional or accidental may be lost/stolen. Monitoring may be difficult. 100% update may be difficult. Consider. Patch/update, continuous action. General network protections, for example network segmentation, firewall devices, network intrusion prevention or detection. Host protections, antivirus, host IPS, host firewall, disk encryption. Monitor logs, alerts, track location. Educate users, anti-phishing campaign detecting attacks. Apply to all general-purpose computing systems servers, database, distributed, cloud-based, web-based. Application servers, file servers, domain controllers, print servers, network service servers, for example, DNS, DHCP, etc. centrally managed/controlled. Limited access/functionality. Likely to be in a tightly controlled network segment. May be exposed to external communication/services. Updates may be delayed due to operational need. May exist for long periods, risk of being outdated. High traffic volume makes monitoring more difficult. Consider targeted network protections, server-specific rules, restricted ports/protocols, strong remote access mechanisms. Configuration and change management. Monitor logs, alerts, targeted to server functions. Hosted on servers, cloud, distributed, etc. Inherits platform vulnerabilities. Typically contains large quantities of valuable information. Typically requires high-speed operation with large number of transactions. Inference. Aggregation. Data mining. High-value target. Consider input validation. Robust authentication/access control. Output throttling. Anonymization. Tokenization. Typically embedded, limited function hardware. Interfaces between logical, computer, space and the physical world. Includes sensors, motors, actuators, valves, gauges, etc. Supervisory control and data acquisition, SCADA distributed control systems, DCS's programmable logic controllers, PLCs. Limited functionality. Limited protections. Long lifespan, become outdated, susceptible to misuse/error. Highly susceptible to denial of service, DOS, attacks. Attacks can produce physical effects. Often unintended in remote locations. Consider isolated network infrastructure. Robust network connection restrictions and monitoring. Highly segmented network. Protect communication channels. Robust configuration control. Components hosted by a cloud service provider, CSP. CSP assumes specific security responsibilities, the remainder stay with the data owner. Typically high reliability, speed, capacities. CSP to data owner relationship is governed by a contract and/or service level agreements, SLAs. On-demand self-service. Broad network access. Resource pooling. Rapid elasticity. Measured service. Multi-tenancy. Software as a service, SaaS platform as a service, PaaS infrastructure as a service, IaaS network as a service, NaaS. Private. Exclusive use by a single organization. On or off premises. Community. Provision for exclusive use by a community of users. Public. Open use by general public. Hybrid. Combination of two or more deployment models. Inherently exposed to external communication/access. Misconfiguration a major risk. May exist for long periods, risk of being outdated, gap between CSP and data owner security controls. Consider reputable cloud service provider that supplies security information/testing results. Well-trained system administrators. Robust configuration control/change control. File and communication encryption. Well-managed identity and access controls. Nodes and processors operate independently. Storage and processing spread across multiple components. Nodes pass messages to coordinate and communicate. Example, traditional telephone. Switches operate independently. Coordinate to pass calls between them. Lack of central control/monitoring. Data elements may be lost if nodes fail. Inconsistent security levels between nodes is possible. Susceptible to communication failures, compromise, or denial of service, DOS. Consider standard security rules for nodes to enter distributed network. Communication control, encryption, and redundancy. Node backup and data sharing between nodes. Generally small form factor, embedded hardware. Limited functionality, OS may interface with the physical world. Pervasive and often connected to general purpose networks. Function/accessibility may be unclear to owner/user. Limited vendor support for updates. Little to no onboard security capability. Poor code management due to rapid development cycles. May contain limited or weak security implementations on standard protocols, for example Bluetooth, Wi-Fi. Consider isolated on private networks with controlled access. Products selected for security features and updatability. Product security/penetration testing. Disable unneeded functions. Applications or data accessible and manipulated through a web browser or web service. Often connects to a data source database that may be on or off platform. Uses standard protocols and interface languages. Connections are typically dynamic. Accessibility to network communication/access. Use of obsolete protocols/encryption. Code/configuration errors that expose components or data. Consider protect system behind firewalls and access controls. Limit and monitor communication protocols. Scan, evaluate, and assess interfaces and code, HTML, Java, scripts, etc. Tightly control configuration and change management. Ensure platform is security configured. Phones, tablets, wearable devices. Portable, small form factor. Limited functionality. Embedded OS typically contains limited amounts of data. Connected, cellular, Wi-Fi, Bluetooth, tethering designed for single user. Laptops, personal computers. Portable, medium form factor. Full-featured operating system. Capabilities similar to a desktop. May contain large amounts of data. Multi-user capable. Connected, Wi-Fi, Bluetooth, tethering, possibly cellular. Are laptops mobile systems? Opinions may vary, wide gray area depending on the particular capabilities and configuration of a device. Share physical vulnerabilities with other device types. Capable of more onboard controls, for example, traditional computer host protections, logging, monitoring, access controls. Mitigation mechanisms are different from other device types. Some tablets cross the line between laptop characteristics and embedded mobile device characteristics. Loss or theft. Weak access controls configured. Unencrypted data. Communication interception or eavesdropping. Limited onboard security services and monitoring. Consider mobile device management, MDM, installed. Device tracking, wiping, software control, policy enforcement. Activate screen lock and high complexity passcodes or biometrics. Ensure devices encrypted. Tunnel communications through VPN architecture. Limit software/apps installed to trusted packages. Prevent jailbreak or rooting devices. Do not connect to public networks, for example, coffee shop, hotel. For laptops. Apply all traditional computer system protections, for example, AV, FW, host IPS, etc. Ensure encryption is activated. Ensure strong passwords, biometrics, or two-factor authentication on all user accounts. Activate anti-theft function or tracking functions if available. Tunnel mobile communications through VPN. Do not connect to public networks, for example, coffee shop, hotel. Computing platform with a dedicated function. Limited function/specialized OS. Limited processing power. Long service life in many applications. Includes system on a chip, SoC architectures. Typically include special device categories. IoT, ICS, mobile devices. Highly diverse in nature. Specialized computing versus general purpose computing. Limited function design does not include all full monitoring and security control implementation. Limited access controls. Limited ability to update, vendor support often time limited. Consider limit access to devices. Limit communications to devices. Disable unnecessary/unneeded components/features/communications. Isolate on dedicated networks if connected. Monitor external communications with exterior sensors, for example, network taps, sensors. Apply vendor updates when available. The National Federal Amalgamated Corporation, NFAC, is developing a new customer-facing application for amalgamated data. The initial design includes the following elements. Database servers within the NFAC data center that store customer private and sensitive data elements. Application servers within the NFAC data center that access the database servers and are accessed by NFAC employee workstations. Employee workstations, some desktop, some laptop, are used by NFAC employees to access the application servers to access, upload, modify, and delete sensitive customer data. Web servers located with a cloud provider that access fact databases and applications to deliver data to external customers through a web browser. Mobile applications distributed to customers for installation on Android and Apple devices that provide customer access via a mobile application service hosted by the same cloud provider hosting the web servers. Instructions. Consider the scenario and the vulnerabilities, mitigations, and controls discussed in the preceding modules. Each of the system types listed in the scenario have inherent strengths and weaknesses. For each item, identify potential risks or weakness and one or more controls or mitigation consistent with the access requirements listed in the scenario. Activity: designing security into an architecture. Instructions, continued. Example: database servers. Risk: database servers contain bulk-sensitive data and may be targeted by adversaries. Control: database servers will be placed on a protected network segment and network access controls will prevent access to the database server for any connection except from authorized application servers. Module 6. Cryptography. Module objectives. 1. Understand key terms associated with cryptography. 2. Understand how security services such as confidentiality, integrity, authenticity, non-repudiation, and access control are addressed through cryptography. 3. Understand basic cryptography concepts of symmetric and asymmetric. 4. Describe hashing algorithms and digital signatures. 5. Understand the importance of key management. 6. Understand cryptanalysis methods. Cryptography services. Confidentiality. Integrity. Authenticity. Non-repudiation. Access control. Data protection. End-to-end encryption. Generally performed by the end user within an organization. The data is encrypted at the start of the communications channel or before and remains encrypted until it is decrypted at the remote end. Link encryption. Encrypts all of the data along a communications path. Communications nodes need to decrypt the data to continue routing. Cryptographic evolution. Cryptographic techniques. Manual. Mechanical. Electromechanical. Electronic. Quantum cryptography. Key encryption concepts and definitions. Stream-based ciphers. A key stream, sequence of bits used as a key, is generated and combined with the plaintext using an exclusive or XOR operation. Statistically unpredictable and unbiased. Not linearly related to the key. Operates on individual bits or bytes. Functionally complex. Long periods with no repeats. Cryptographic operation for a stream-based cipher. Plaintext is XO-read with a seemingly random key stream to generate ciphertext. It is seemingly random because the generation of the key stream is usually controlled by the key. Exclusive or XOR. 1. Convert letters into C equals ASCII 67. Binary value 67 binary equals 01000011. I equals ASCII 65. 65 binary equals 01000001. 2 XOR values 010011. 01000001. XOR calculation. Compare two binary values. If both values are same, the output is 0. If they are different, the output is 1. Block ciphers. A block cipher operates on fixed-size blocks of text. The size of the block affects the strength of the cryptographic implementation. As plaintext is fed into the cryptosystem, it is divided into blocks of a preset size. Often a multiple of the ASCII character size, 64, 128, 192 bits, etc. Block ciphers, continued. Key length. Important aspect of key management to consider when generating and using cryptographic keys. The longer the key, the more key space it represents. Block size. Block ciphers operate on a fixed length string of bits. Typically 64 bits, or multiples of 64 bits. Initialization vectors for -y they are needed. Encrypting the same plaintext using the same key always produces the same ciphertext. Encrypting the same message with different keys may produce discernible patterns. And 4 is a random value added to the plaintext message before encrypting so that each ciphertext will be substantially different. Kirchhoff's principle. High work factor. Measured in units such as hours of computing time. Cost in dollars of breaking the encryption. If the work factor is sufficiently high, The encryption system is considered to be practically or economically unbreakable. Substitution ciphers. The process of substituting one letter for another based upon a crypto variable involves shifting positions in the alphabet of a defined number of characters. Caesar cipher and Vigenère cipher involves using a scrambled alphabet to substitute one letter for another. Enigma machine. Transposition ciphers. Cryptosystems that use transposition or permutation rely on concealing the message through the transposing of or interchanging the order of the letters. Rectangular substitution tables. Monoalphabetic and polyalphabetic ciphers. Monoalphabetic cipher, polyalphabetic cipher. Developed circa 15th century. Encrypt the plaintext feedback using a key of 3241 Kuwait. Running key cipher. Use the value of plaintext letters and a value of key based on a shared book. Value of message, this message, plus value of key on periodic, equals value of ciphertext. One-time pads. The only cipher system asserted is unbreakable. Both sides have same pad of key values. Truly random key values. Keys are only used once. Steganography. Plaintext hidden/disguised. Prevents a third party from knowing that a secret message exists. Traditionally accomplished in a number of ways. Physical techniques. Modern steganography. Null ciphers. Null cipher. Plaintext is mixed with large amounts of non-cipher material. A simple form of steganography. Null cipher. Are you deaf, Father William? William Carroll, 1876. Are you deaf, Father William? The young man said, did you hear what I told you just now? Excuse me for shouting. Don't waggle your head like a blundering, sleepy old cow. A little maid dwelling in Wallington town is my friend, so I beg to remark. Do you think she'd be pleased if a book were sent down entitled The Hunt of the Snark? Pack it up in brown paper. The old man cried, and seal it with olive and dove. I command you to do it. He added with pride, nor forget, my good fellow, to send her beside Easter greetings, and give her my love. Advantages and disadvantages of symmetric algorithms. Out-of-band key distribution. Out-of-band key distribution. Examples of symmetric algorithms. System 97 printing machine for European characters. Codename Purple. Mode usage. Electronic code book, ECB, very short messages, less than 64 bits in length, such as transmission of a day key. Cipher block chaining, CBC, authentication. Cipher feedback, CFB, authentication. Output feedback, OFB, authentication. Counter center, used in high-speed applications such as IPsec and ATM. Electronic codebook, ECB mode. Cipher block chaining, CBC mode. Using symmetric block ciphers to simulate stream ciphers. Cipher feedback, CFB mode. Output feedback, OFB mode. Counter center mode. Electronic codebook, ECB mode. Each block of plaintext is encrypted independently using the same key. Only used for small messages, smaller than 64 bits. Cipher block chaining, CBC mode. Cipher feedback, CFB mode. Output feedback, OFB mode. Counter mode center. The Data Encryption Standard, DES. Horst Feistel had developed a family of algorithms that had a core principle of taking the input block of plaintext and dividing it in half. Then, each half was used several times through an exclusive or operation to alter the other half, providing a type of permutation as well as substitution. A Feistel algorithm became the data encryption algorithm used for day. DEA algorithm is symmetric block cipher, 64-bit blocks, 16 rounds, 56-bit effective key length. Double day, 2-day. Given today's technology, day key is too short to provide adequate protection. One of the first alternatives to create a stronger version of day was to double the encryption process. Meet in the middle attack on 2-day. Triple day, 3-day. Triple day was designed to operate at a relative strength of 2112 using 2, or 3, different keys to perform the encryption. This effectively rendered a key with a 168-bit strength, as there are always 3 iterations done with the keys. Counter mode with cipher block chaining message authentication code protocol, CCMP. CCMP is an authentication protocol that forms part of the 802.11i standard for wireless local area networks. How CCMP works. ICE processing in CCMP must use ICE 128-bit key and 128-bit block size. CCMP use of 128-bit keys and a 48-bit 4 minimizes vulnerability to replay attacks. The center component provides data privacy. The cipher block chaining message authentication code component produces a MIC that provides data origin authentication and data integrity for the packet payload data. Rindale. The Rindale algorithm can be used with block sizes of 128, 192, or 256 bits. 4 major operations: byte sub, shift row, mix column add, round key. Other symmetric algorithms. International Data Encryption Algorithm, IDEA 128-bit key 64-bit blocks. CAS 128 key length between 40 and 128 bits. 12 and 16 rounds. Safer uses 64-bit, Safer SK64, or 128-bit blocks. Safer SK128 Blowfish uses variable key sizes, from 32 up to 448 bits on 64-bit blocks. Other symmetric algorithms, continued. Twofish can operate with keys of 128, 192, or 256 bits on blocks of 128 bits. RC4 commonly used stream-based cipher. RC5 RC6 key size can vary from 0 to 2040 bits, the number of rounds 0 to 255. International Data Encryption Algorithm, IDEA uses a 128-bit key and operates on 64-bit blocks. IDEA does 8 rounds of transposition and substitution using modular addition and multiplication and bitwise XOR. CAST. CAST 128 can use keys between 40 and 128 bits in length and will do between 12 and 16 rounds of operation, depending on key length. Secure and fast encryption routine Safer. All of the algorithms in Safer are patent-free. The algorithms work on either 64-bit input blocks, Safer SK64, or 128-bit blocks, Safer SK128. Blowfish. Extremely fast cipher and can be implemented in as little as 5K of memory. Operates with variable key sizes, from 32 up to 448 bits on 64-bit input and output blocks. Twofish. Was one of the finalists for the ICE. Can operate with keys of 128, 192, or 256 bits on blocks of 128 bits. Performs 16 rounds during the encryption/decryption process. Very adaptable product useful for many applications. The key for RC5 can vary from 0 to 2040 bits. The number of rounds it executes can be adjusted from 0 to 255. The length of the input words can also be chosen from 16, 32, and 64-bit lengths. The algorithm operates on 2 words at a time in a fast and secure manner. If RC4 is used with a key length of at least 128 bits, there are currently no practical ways to attack it. The published successful attacks against the use of RC4 in WEP applications are related to problems with the implementation of the algorithm, not the algorithm itself. Symmetric algorithms. Advantages and disadvantages of symmetric algorithms. Advantages include fast, secure, confidentiality. Disadvantages include key distribution is very difficult, not able to provide integrity, authenticity, non-repudiation of origin, access control, and digital signatures. Require both sender and receiver to share the same key. Challenges with secure key distribution. Scalability. Out-of-band key distribution. Out-of-band key distribution. Cryptovariable. Asymmetric algorithms. Asymmetric algorithms. Based on the use of a pair of mathematically related keys. Relies on hard mathematical problems and one-way functions. A process that is much simpler to go in one direction, forward, than to go in the other direction, backward or reverse engineering. The process to generate the public key, forward, is fairly simple. To learn the private key from knowledge of the public key and computationally infeasible. Asymmetric algorithms, continued. Using public key cryptography to send a confidential message. Open message. When a message is encrypted with the private key of a sender, it can be opened or read by anyone who possesses the corresponding public key. When a person needs to send a message and provide proof of origin, non-repudiation, he can do so by encrypting it with his own private key. The recipient then has some guarantee that the message did originate with the sender. Using public key cryptography to send a message with proof of origin. Confidential messages with proof of origin. Rivest-Shamir-Adleman, RSA, algorithm. RSA is based on the mathematical challenge of factoring the product of two large prime numbers. 3 primary attack approaches. Diffie-Hellman algorithm. Used to enable two users to exchange or negotiate a secret symmetric key that will be used subsequently for message encryption. Does not provide for message confidentiality, but it is extremely useful for applications such as TLS and IPsec. Based on discrete logarithms. El-Gamal. Included the ability to provide message confidentiality and digital signature services. Based on the same mathematical functions of discrete logs. Elliptic curve cryptography, ECC. The ability to use much shorter keys for ECC implementations provides savings on computational power and bandwidth. This makes ECC especially beneficial for implementation in smart cards, wireless, and other similar application areas. Elliptic curve algorithms provide confidentiality, digital signatures, and message authentication services. Advantages and disadvantages of asymmetric key algorithms. Possible to send a message across an untrusted medium in a secure manner without the overhead of prior key exchange or key material distribution. Access control. Confidentiality. Integrity. Non-repudiation. Authenticity. No scalability problem. Activity, asymmetric cryptography. 1. What must the key holder do to allow for the transmission of a confidential message? 2. Identify one or more advantages of asymmetric cryptography. 3. Identify one or more disadvantages of asymmetric cryptography. 4. Describe RSA. Activity, asymmetric cryptography, continued. Answers. 1. Keep their private key confidential. 2. It makes it possible to send a message across an untrusted medium in a secure manner without the overhead of prior key exchange or key material distribution. 3. Extremely slow. 4. RSA is based on the mathematical challenge of factoring the product of two large prime numbers. Hybrid cryptography and cryptographic systems. Message integrity controls, MICs. MICs detect alterations, whether intentional or accidental, to a message during transmission. A MIC is a special value that is calculated based on the message contents and added to the message to be sent. Accomplished through cryptographic functions that perform in several manners, depending on the business needs and level of trust between the parties and systems. Message digests. A small representation of a larger message. Used to ensure the authentication and integrity of information, not the confidentiality. Message authentication code, MAC. A small block of data that is generated using a secret key and then appended to the message. When the message is received, the recipient can generate his/her own MAC using the secret key and know the message is not changed. Hash Message Authentication Code, HMAC. Hashed MAC implements a freely available hash algorithm as a component, black box, within the HMAC implementation. This allows ease of the replacement of the hashing module if a new hash function becomes necessary. Hashing. Accepts an input message of any length and generates a fixed length output. Operation of hash functions. 5 key properties of a hash function. Uniformly distributed. Collision resistant. Difficult to invert. Computed on entire message. Deterministic, same input always produces same digest. MD5 message digest algorithm. The most widely used hashing algorithm and is described in RFC 1321 but no longer considered secure. MD5 generates a 128-bit digest from a message of any length. It processes the message in 512-bit blocks and does 4 rounds of processing. Secure Hash Algorithm, SHA and SHA-1. SHA was developed by NIST. SHA-1 operates on 512-bit blocks and can handle any message up to 264 bits in length. The output of SHA-1 is 160 bits in length, not considered good practice. Recommended use of SHA-512. The processing includes 4 rounds of operations of 20 steps each. Secure Hash Standard, SHA-3. The new hash algorithm is based on the Kekik algorithm and will be named SHA-3. It will be described in FIPS 202, draft as of April 2015, and will augment the hash algorithms currently specified in FIPS 180-4, the secure hash standard. Other hash algorithms. Haval, variable length output. Ripened 160, European standard. The output may be 128, 160, 192, 224, or 256 bits, and the number of rounds may vary from 3 to 5. Haval operates 60% faster than MD5 when only 3 rounds are used and is just as fast as MD5 when it does 5 rounds of operation. The birthday paradox/birthday attack. Once there are more than 23 people together, there is a greater than 50% probability that 2 of them share the same birthday. The likelihood of finding a collision for 2 messages and their hash values may be a lot easier than may have been believed. It would be very similar to the statistics of finding 2 people with the same birthday. Rainbow Table uses this predictability against hashing systems. Digital signatures, non-repudiation. Provides assurance that the message comes from the person who claims to have sent it. Has not been altered, both parties have a copy of the same document. The sender cannot claim that he or she did not send it. Digital signature standard, DSS. A digital signature is based on a public key asymmetric algorithm. Does not provide for confidentiality of the message through encryption and is not used for key exchange. Digital signatures. Uses of digital signatures. A digital certificate is an electronic document that asserts authenticity and data integrity that is tied to a sender. Digital signatures are used to sign emails, e-commerce transactions, software and software patches, and digital certificates. Many governments and courts recognize digital signatures as a verifiable form of authentication. Combine everything? Applying cryptography and key management. Cryptographic lifecycle. A cryptographic function is broken when one of the following conditions is met. For a hashing function, collisions or hashes can be reliably reproduced in an economically feasible fashion without the original source. When an implementation of a hashing function allows a side-channel attack. For an encryption system, a cipher is decoded without access to the key in an economically feasible fashion. When an implementation of an encryption system allows unauthorized disclosure or alteration of information. Private key has been compromised. Algorithm/protocol governance. Cryptography policies, standards, and procedures should minimally address approved cryptographic algorithms and key sizes. Transition plans for weakened or compromised algorithms and keys. Procedures for the use of cryptographic key generation, escrow, and secure destruction. Incident reporting. Issues surrounding cryptography. As part of risk analysis, it is important to understand how cryptography can be misused so that appropriate security mitigation can be applied. Cryptographic protection is implemented for preventing software and media piracy or corruption of software, digitally signed software and software patches. Digital rights management systems, DRMS, require a design and governance to protect intellectual property and individual privacy while ensuring an individual's fair use of the intellectual property. International export controls. Most countries regulate the use of cryptographic tools used by their citizens. Most laws that control the use of cryptography are based on key length. Dual-use good, can be used for both commercial and military purposes. This is because key length is one of the most understandable methods of gauging the strength of a cryptosystem. Public key infrastructure, PKI, a set of system, software, and communication protocols required to use, manage, and control public key cryptography. It has core primary purposes. Publish public keys/certificates. Certify that a key is tied to an individual or entity. Provide verification of the validity of a public key. Provide services such as confidentiality, integrity, authenticity, non-repudiation, and access control. Certification/certificate authority CA. Binds entities to their public keys. Signs an entity's digital certificate to certify that the certificate content accurately represents the certificate owner. X509 Certificate. Certificate revocation. Certificate revocation is required if private key has been compromised. Provides updates on non-valid certificates, in other words, tells certificate holders not to use public key. Key management and key management practices. Key recovery. Dual control. 2 or more people required working in cooperation. Split knowledge. Specific information known only to one individual that must be combined with knowledge held by another individual. Key escrow. Storing key with a trusted party. Creation of keys. Automated key generation. Truly random. Random. Asymmetric key length. Key wrapping and key encrypting keys. KEX. KEX are used as part of key distribution or key exchange. The process of using a KEX to protect session keys is called key wrapping. Key wrapping uses symmetric ciphers to securely encrypt a plaintext key with associated integrity information and data. Key distribution. Keys can be distributed in a number of ways. Example: out-of-band key exchange, key wrapping, key storage and destruction. Methods for protecting stored key material include trusted, tamper-proof hardware security modules, passphrase-protected smart cards, key wrapping the session keys using long-term storage keys, splitting cipher keys and storing in physically separate storage locations, protecting keys using strong passwords/passphrases, key expiry, and the like. At the end of life cycle of keys, they must be securely destroyed. Cryptanalysis, methods of cryptanalytic attacks. Brute force attacks. Ciphertext-only attack. One of the most difficult because the attacker has so little information to start with. All the attacker starts with is some unintelligible data that he suspects may be an important encrypted message. The attack becomes simpler when the attacker is able to gather several pieces of ciphertext and thereby look for trends or statistical data that would help in the attack. Known plaintext. The attacker has access to the ciphertext and the plaintext versions of the same message. The goal of this type of attack is to find the cryptographic key that was used to encrypt the message. Once the key has been found, the attacker would then be able to decrypt all messages that had been encrypted using that key. Chosen plaintext. The attacker knows the algorithm used for the encrypting or has access to the machine used to do the encryption and is trying to determine the key. This may happen if a workstation used for encrypting messages is left unattended. The attacker can run chosen pieces of plaintext through the algorithm. Chosen ciphertext. Similar to the chosen plaintext attack in that the attacker has access to the decryption device or software and is attempting to defeat the cryptographic protection by decrypting chosen pieces of ciphertext to discover the key. Sometimes called the lunchtime attack. An adaptive chosen ciphertext would be the same, except that the attacker can modify the ciphertext prior to putting it through the algorithm. Sometimes called the midnight attack. Linear and differential cryptanalysis. Linear cryptanalysis is a known plaintext attack that requires access to large amounts of plaintext and ciphertext pairs encrypted with an unknown key. It focuses on statistical analysis against one round of decryption on large amounts of ciphertext. Differential cryptanalysis is a chosen plaintext attack that seeks to discover a relationship between ciphertexts produced by two related plaintexts. It focuses on statistical analysis of two inputs and two outputs of a cryptographic algorithm. Implementation attacks. Some of the most common and popular attacks against cryptographic systems due to problems with their implementation ease and reliance on system elements outside of the algorithm such as random number generators. Replay attack. Disrupts and damages processing by the attacker by resending repeated files to the host. If there are no checks such as timestamping, use of one-time tokens or sequence verification codes in the receiving software, the system might process duplicate files. Birthday attack. The point of the birthday attack is that it is easier to find two messages that hash to the same message digest than to match a specific message and its specific message digest. Factoring attack. Because RSA uses the product of large prime numbers to generate the public and private keys, this attack attempts to find the keys through solving the factoring of these numbers. Attacking the random number generators. This attack was successful against the SSL installed in Netscape several years ago. Because the random number generator was too predictable, it gave the attackers the ability to guess the random numbers. Short initialization vectors led to compromise of WEP since the fourth was not random enough. Other cryptographic attacks include algebraic, timing, power analysis, frequency analysis, statistical analysis, social engineering, brute force, dictionary attacks, rainbow tables. Accessing temporary files. Most crypto systems will use temporary files to perform their calculations. If not deleted and overwritten, they may be compromised and lead an attacker to the message in plaintext. Social engineering for key discovery. Through coercion, bribery, or befriending people in positions of responsibility, spies gain access to systems without having any technical expertise. This is the most common type of attack and usually the most successful. Module 7. Physical security. Module objectives. 1. Apply security principles to site and facility design. 2. Implement and manage physical security controls. 3. Implement and manage physical controls in wiring closets and intermediate distribution facilities. 4. Implement and manage physical controls in server rooms and data centers. 5. Implement and manage physical controls in media storage facilities. 6. Implement and manage physical controls for evidence storage. 7. Implement and manage physical controls in restricted areas. Module objectives, continued. 8. Implement and manage physical controls in work areas. 9. Implement and manage environmental controls for utilities and power. 10. Implement and manage controls for heating, ventilation, and air conditioning, HVAC. 11. Implement and manage environmental controls. 12. Implement and manage environmental controls for fire prevention, detection, and suppression. Physical security. Physical security plans and infrastructure are often designed, implemented, and operated by physical security specialists. Physical security infrastructure is typically controlled outside of IT or IT security control. The CISSP must understand physical security fundamentals in order to assess the risk reduction value of physical security controls. Communicate physical security needs to physical security managers. Identify risks to information security due to physical security weaknesses. Apply security principles to site and facility design. Physical design should support confidentiality, integrity, and availability of information systems. Physical design must consider human safety and external factors as well. Physical design that supports confidentiality, integrity, and availability, CIA. Physical design protects information systems from unauthorized access. Provides for auditing or observation of sensitive physical access. Includes identification of subjects in sensitive areas. Ensures robust services, for example, power, cooling, to information systems. Physical design that supports human safety. Emergency alarms, audible, visible egress routes. Safety equipment. Emergency power or equipment shutoffs. Equipment lockouts. Site and facility design considerations. Personnel policy and procedure. Personnel screening. Workplace violence prevention. Response protocols and training. Mail screening. Shipping and receiving. Property ID and tracking. Parking and site security. Site and building access control. Video surveillance. Internal access control. Infrastructure protection. On-site redundancy. Structural protections. Implement and manage physical security. Conduct a physical risk assessment, Domain 1 human action, natural disaster, industrial accident, equipment failure, etc. Develop layered physical protections commensurate with the risk assessment. For example, embassy-level protections versus a small remote office. Physical risk controls will impact information system design. For example, weak physical controls may necessitate more complex information system protections to compensate. Physical protections require monitoring and auditing. Perimeter security controls. Surrounding areas. Roadways. Waterways. Geography. Lines of sight. Consider. Facility visibility from roads. Potential for vehicle-borne threats. Vehicular and pedestrian access point locations. Fencing, perimeter landscaping, natural. Perimeter security controls, continued site entry/exit points. Vehicular. Public/customer/visitor. Staff/employee. Delivery/truck. Pedestrian. Consider. Access controls. Surveillance. Lighting. Intrusion detection. Barrier/traffic control. Perimeter security controls, continued external facilities. Parking structures/lots. Utilities components. Electric transformers/lines. Telecommunications. Landscaping. Consider. Lighting. Surveillance. Intrusion detection. Lines of sight. Perimeter security controls, continued operational facilities. Where employees work. Where information technology operates. Consider. Exterior lighting and surveillance. Building materials. Doors, locks, windows, walls. Entry/exit points and access controls. Staff/employee entrance. Public/customer entrance. Delivery entrance. Sensor/intrusion detection. Perimeter security controls, typical control types. Lighting. bright enough to cover target areas. Limits shadow areas. Sufficient for operation of cameras, must be coordinated with camera plan. Surveillance/camera. Narrow focus for critical areas. Wide focus for large areas. IR/low light in unlit areas. Monitored and/or recorded. Dummy cameras. Perimeter security controls, typical control types, continued intrusion detection. Cut/break sensors. Sound/audio sensors. Motion sensors. Barriers. Fixed barriers to prevent ramming. Fixed barriers to slow speeds. Deployable barriers to block accessways. Fencing/security landscaping. Slows and deters. Should not impede monitoring. Perimeter security controls, typical control types, continued building material security examples. High security glass. Steel/composite doors. Steel telecommunications conduit. Secure walls. True floor-to-ceiling walls, wall continues above drop ceiling anchored framing material. Solid walls/in-wall barriers. Lock security examples. Available in varying grades. Physical key locks. Mechanical combination locks. Electronic combination locks. Biometric locks. Magnetic locks. Magnetic strip card locks. Proximity card locks. Multi-factor locks, for example, card plus PIN. Internal security controls. Controls for human safety. Visible and audible alarms, fire suppression, response plan/training, emergency shutoffs. Controls to manage access. Door locks, for example, magnetic, card key, mechanical key, combination lock access point security, for example, man traps, limited ingress, alarmed emergency egress multi-factor access, for example, key card plus PIN for room entry internal monitoring. Physical access control system/monitor, for example, records key card use video surveillance/cameras. RF monitoring. Implement site and facility security controls. Wiring closets/intermediate distribution facilities. Server rooms/data centers. Media storage facilities. Evidence storage. Restricted area security. Utilities. Heating, ventilation, and air conditioning, HVAC fire prevention, detection, and suppression. Environmental issues. Facilities, components. Entrance facility. External communications center facility. Phone, network, special connections. May house ISP/provider equipment. Equipment room. Primary communication hub for facility. Houses wiring/switch components. May be combined with entrance facility. Backbone distribution. Connects entrance facility, equipment room, and telecommunication rooms. Facilities, components, continued telecommunications room, wiring closet serves a particular area of a facility. Floor, section, wing, etc. terminates local wiring into patch panels. Backbone distribution is broken out to individual connections, for example, switch horizontal distribution system. Cables, patch panels, jumpers, cable. Facilities, protections. Security protections. Rooms must be secured against unauthorized access. Access to rooms should be monitored/recorded. Secondary locks on equipment/racks. Rooms may share space with non-IT equipment and require access by non-IT staff. Conduit or tamper protections for wiring. Environmental protections. Protection from lightning/surge. Backup power UPS heating/cooling/airflow. Critical and enclosed spaces. Appropriate fire detection/suppression. Emergency shutoffs for high power connections. May not be necessary in all closets. Server rooms/data centers. Similar security and environmental protections to wiring closets. Access point security and access monitoring is a critical concern. Rack or equipment level locking for shared spaces. Especially in shared spaces. Power/surge/uninterruptible power supply, UPS, equipment is tailored to the operating equipment. Human safety becomes an issue with power levels in most server rooms. Emergency shutoffs and non-conductive hooks/gloves are important for human safety. Appropriate fire detection/suppression must be considered. For example, sprinkler is inappropriate for electrical fires typically maintained at a higher level of physical security than the rest of the facility. Media storage facilities. Media may be stored on-site and off-site from the main facility. Off-site storage should duplicate critical media. Access control is strictly limited and monitored, often limited to archivist temperature/humidity should be consistent with media storage requirements. As media types evolve, this must be continually reassessed. Fire protection at both room and container levels. Evidence storage. Access strictly limited and monitored. Individual lockers/secure containers for investigation/investigators. Tamper evidence seals available for evidence bags/containers. Maintaining chain of custody is critical to prove evidence has not been modified or tampering has not occurred. Evidence protected against damage/theft. Environmental protections should be commensurate with evidence type stored, for example, paper, digital media. Restricted area security. Includes secure facilities and classified workspaces. Extremely high access control protections and logging of access. May include audio protections against eavesdropping. May include enhanced visual screening from exterior spaces. May include protection against the detection of electromagnetic emissions from equipment. Utilities. Power. Redundant power input from utilities. Redundant transformers/power delivery. Backup generators. Battery backups. Dual power infrastructure within data centers. Backup sources must be tested/exercised. Backup sources must be sized appropriately and upgraded when load increases. Telecommunications. Multiple service provider inputs. Redundant communication channels/mechanisms. Redundancy on key equipment, eliminate single points of failure water/sewer. Cooling/human habitation. Risk of leaks/damage to equipment. Supports most building-wide fire suppression plans. Utility safety. Generators, battery backups, and data center power feeds may carry very high electrical loads that are inherently dangerous. Emergency power shutoffs in high-load areas. Safeguard human life in case of electrocution. Big red button safeguard equipment in case of overload. Automated shutoff safeguard humans and equipment in emergencies. Flooding/sprinkler activation. High-load areas should provide access to non-conductive gloves/equipment and push/pull rods in case of emergency. Heating, ventilation, and air conditioning. HVAC high-density equipment requires adequate cooling and airflow. Cooling must be designed match the equipment/space to be cooled. High-capacity rooms, for example, operations center, must have sufficient airflow for the number of human occupants. CO2 danger air should be filtered for contaminants, natural or intentionally introduced. Fire prevention and detection. Human training and awareness is critical to prevention. Sensors, IR, temperature, smoke, can detect conditions leading up to a fire as well as fire initiation. Smoke detectors include optical, photoelectric, and physical process. Ionization fire detectors include infrared and ultraviolet detectors. Fire suppression. Buildings should be equipped with one or more types of fire suppression systems that include installed and handheld. Handheld extinguishers are typically chemical agent-based with either wet or dry chemicals. Two main types of installed suppression systems, water-based and gas-based. Water-based. Effective for common material fires, for example, wood, paper, building materials safe for human spaces. Damages equipment. Ineffective for electrical or petroleum fires. Typically cheaper than gas-based. Gas-based. Effective for any fire type. Typically safe for equipment. May be dangerous to humans in enclosed spaces, depending on type, costly to install and maintain compared to water-based. Water-based system types. Wet pipe. Most common, water in pipes, heat-activated sprinkler heads. Dry pipe. Pressurized gas in pipes, water released when activated, slight delay, less danger of pipe leaks/freezing. Pre-action. Combines wet and dry pipe actions. Deluge. Pre-action but with open sprinkler heads. Gas system examples. Hydrofluorocarbon. Halon, older type, mostly gone FM200. Inert gas, for example, argon/nitrogen argonite. Energon. Aerosol. Aerok. Environmental issues include hurricane, forest/wildfire, flooding, tornado, earthquake, mudslide. Module 9. Domain review. Domain summary. Application of security engineering and architecture principles is a key element to any system lifecycle. Security models are used as templates for system security behavior and design. Security control frameworks are employed to ensure consistent and complete application of security functions across an environment. Various types of systems have inherent security strengths and weaknesses that must be understood to ensure they are properly employed. The history of cryptography is very long, but over the last 50 years or so, cryptography has become an integral and necessary part of security implementations. Cryptography can be very effective in providing some key security services such as confidentiality, integrity, authenticity, proof of origin, non-repudiation, and access control. There are basic fundamental ways to do cryptography: stream and block ciphers. Symmetric key cryptography is very fast, but has problems related to key distribution and scalability. Asymmetric key cryptography is very slow but solves the problems related to key distribution and scalability. Hashing, which is defined as one-way encryption, can be very useful in addressing integrity of stored and transmitted information. Digital signatures can achieve non-repudiation of origin and non-repudiation of delivery. Key management and key management techniques are the most important aspects of secure cryptography implementations. There are many cryptanalysis attacks that try and break cryptography systems. Physical security is an important element to ensure information systems are protected. Domain review questions. 1. Requirements definition, design, implementation, and operation are examples of what type of system and security engineering processes? A. Technology processes. B. Acquisition processes. C. Design processes. D. Technical processes. The correct answer is D. A is incorrect terminology. B and C are specific processes, not types of processes. 2. One security model includes a set of rules that can dynamically restrict access to information based upon information that a subject has already accessed in order to prevent any potential conflict of interest. This model is known as the A. Biba model. B. Brewer/Nash model. C. Graham-Denning model. D. Harrison-Rizzo-Ullman model. The correct answer is B. A, C, and D are models that describe an information system's rules for operation, but those rules are applied universally. The Brewer/Nash model is the only model that explicitly addressed conflicts of interest. 3. Select the best answer. Inheritable or common security controls are characterized as A. Controls that are passed down from older systems to new systems through code sharing. B. Introduces unacceptable risk in most systems. C. Controls that are never assessed in an operational environment. D. Controls that are provided from one system to another in an operational environment. The correct answer is D. D is the correct definition of the term. A, B, and C are not types of controls. All controls must be assessed whether inherited or not, and while inheritable controls may introduce risk if not operating properly, they do not generally introduce unacceptable risk, which makes D a better answer. 4. 3 common types of industrial control systems include A. Supervisory control and data acquisition, distributed control systems, programmable logic controllers. B. Supervisory control and data anonymization, distributed control systems, programmable logic capability. C. Supervisory control and data anonymization, distributed chip systems, programmable logic controllers. D. Supervisory control and data acquisition, distributed chip systems, programmable logic capability. The correct answer is A. Items B, C, and D include incorrect terminology. 5. The 4 most common types of sprinkler systems are A. Soaking, wet pipe, dry pipe, and pre-action. B. Wet pipe, dry pipe, deluge, and pre-action. C. Wet pipe, dry pipe, soaking, and hybrid. D. Dry pipe, soaking, deluge, and hybrid. The correct answer is B. Items A, C, and D each contain at least one incorrect element. 6. The key used in a cryptographic operation is also called A. Cryptovariable. B. Cryptosequence. C. Cryptoform. D. Cryptologic. The correct answer is A. The cryptovariable is the correct definition used by cryptologists to describe the key in a cryptography system. 7. Most cryptographic algorithms operate either in block mode or A. Cipher mode. B. Logical mode. C. Stream mode. D. Decryption mode. The correct answer is C. All ciphers either operate on stream mode, 1 bit at a time, or block mode, several bits at a time. 8. Which of the following is not one of the primary objectives of cryptography? A. Non-repudiation. B. Authenticity. C. Data integrity. D. Authorization. The correct answer is D. The 5 services that cryptography can provide are confidentiality, integrity, authenticity, non-repudiation, and access control. Authorization, therefore, is not a service that cryptography can achieve. 9. Another name for symmetric key cryptography is A. Shared. B. Public. C. Key clustering. D. Elliptic curve. The correct answer is A. Symmetric, which means the same, implies that a shared key is required by the sender and the receiver in order to be able to encrypt and decrypt a message or data. 10. How many keys would need to be managed for an asymmetric key system such as RSA with 500 users? N. A. NX2. B. N. N1/2. C. 2 to the power of N. D. N to the power of 2. The correct answer is A. Asymmetric key cryptography algorithms require users to have their private and public key pairs, 2 keys each. For 500 users, each having a key pair, the answer is 1000 or NX2.